Log on, tune in, find out. Another good idea from Cambridge.
The first session of the last day of this conference, and we'll immediately start because we're a little bit late already. And the first speaker is Dennis Lin from the Department of Statistics of the Pennsylvania State University, and he will talk about minimal support designs.
Okay, good morning. Finally, last day. And let me starting with my talk. There's lots of good friends here, old friends and new friends. Let me show you my thing I'm proud most, all right? That's my family. So for those people, just update you, my family. This, you see, I got three daughters. I got three daughters and one son. And this is for her graduation last summer. So two down, one to go. That's the basically the idea. They talk about, one thing get me interested about discrete choice. They talk about heaven is where you have Chinese food, British house, Japanese wife, American salary. That's pretty much like my life at Penn State, actually. All right, I eat Chinese food. I have decent, big British style house at Penn State. My wife, although not Japanese, behave like the Japanese wife. So, and I got American salary. But if you get the wrong combination, that become trouble. It's a hell is a place where you have Chinese salaries, for example, like 20 pounds per day that I got now. You got British food, fish and fry Monday, Wednesday. You got Japanese house, reasonable house but tight. And my wife become American now, so it's so pretty much like what I leave Cambridge last 7 weeks. I'm leaving tomorrow, but nonetheless, even this hell place, I'd like to say thank you very much. It's been pretty. I'm very happy. Reasonably productive last 7 weeks and truly grateful. So thank you so much to the committee, for Rosemary inviting me here and this committee, of course. I pretty proud something else. And thanks Steve for inviting me to give a talk. I've been here 7 weeks. This is my fourth conference, I think. No one asked me to talk except Steve. Really appreciate it. So what I learned 7 weeks. Well, here's my conclusion after 7 weeks stay in Cambridge. Number one, I really don't know design. I mean, there's lots of all kind of problems which I don't understand very well. But even worse, I find I don't understand English. I was confused Z and S with or without E. It's really complicated. And last night I talked to Debian. Where's Debian? Off asleep, all right? What I realized is last night what I find I cannot count. In USA we have 1, 2, 3, 4. Here you have G, 1, 2, 3. Very complicated. It's really cannot count. So really, what I realized, if come to USA, 007 is supposed to be 118, actually, if you read American style. All right. Now, joking apart, let me talk about what I'm going to talk about today. I realized many talks is really great, and I don't understand very well. So I'm going to put the very bottom line, treat everybody as high school kid. We're going to talk about a very simple problem today, and hopefully can help me out. So here's the typical what you have. Here's the input variables, what we call design matrix, your output, set up like that. And this is the design matrix we talk about. So fundamental question is how, if I have a control on those x, y, j, what will you put there? That's basic idea, all right? Now, when sample size is greater than number of parameter estimate, that's conventionally what we have. When they are equal, that's minimum point you have, number of parameter you have is k plus 1. That's called saturate or called minimum point. When it's less than, it's called something called supersaturate, where you have more parameter than number of runs you have. In genetic, it's much, much smaller, all right? So I remember 20 years ago when I published my first supersaturate design paper, the referees just don't believe that will work. But then soon they published something like this, which puzzled me. It's much, much different. So the focus today will be on number of run size equal to number of parameter. So the k variable plus 1 constant terms. So for first order design, looks like this, simple enough. And even worse, I'll make it even simpler. I'm going to talk about 2 levels. I mean, when I was graduate student for Norman Draper, Norman promised me, he said, Dennis, you can get your PhD if you know how to place plus or minus 1 carefully. You can't beat that, right? Simple problem, right? It's just play with 2 numbers, you can get a PhD. So that's what I'm going to do today, just tells you 2 numbers. But when you get to second order, then you probably call this, I'm sorry, this probably M rather than X. The model metric, one emphasis between design metrics and model metrics. Model metric really depends on what model you have, all right? So your information metric become, well, I'll talk about that. It's more like manufact and contracted terms, all right? That's second model I will talk about. Third model I'll talk about is full response service. You got first order, you got contracting, you got interaction, everything put together. So what I'm going to do today is tell you minimum point design, which I did recently, putting together. For first order polynomial design, you see model 1. For second order polynomial, only manufact and contracted without interaction. And finally, with a full response service. I'm pretty sure I'll round out my time, so let me give you my conclusion. So for first order model design, first order saturated design, I want to have minimum point design, meanwhile somehow robust against interaction, which seems impossible, but that's what I'm going to present you today. Secondly, the second order polynomial design, I'm going to introduce something called conference metrics to play with that. DB, okay to come in. Your name just be mentioned. Yeah. He promised you overslept, but he did, yeah, all right. Then the full second order design, response server design is very popular with central composite and box banking design. I did try to make it minimized with the same format. So back to 1990s, I have published a paper called Small Central Composite Design. It takes me 20 years to publish a small box banking design. And if you don't get rid of those forms, Brad Jones have been talking about how to do computer search on that, and we have something to tell you. But it has been a long project. So I predict in 2111 we're going to publish the paper. So it takes a while. It doesn't matter. All right, so that's roughly. So let me go to slide by slide. So for first order design, simple. That's what you have with all elements plus or minus 1. So you can get it with all kind of criteria, right? D optimum, A optimum, whatever. And of course, be careful. There are 26 later. We're going to just spend out very quickly. So try something else, right? Now, what if there's an interaction there? All right, for first order saturated design. What if the interaction? Interaction is going to confound or aliasing, depends on what you have to define. Then what you see is not unbiased estimate. You're going to be misleading. All right? Can I have some first order design really when even there are interaction, my main effect is still unbiased? All right? So first thing think about this is so-called fold over. I have U and I fold over U. Then this early paper paper tells you if V is your interaction, then main effect will orthogonal interaction. Clear? So all I'm doing is put them together, marry them together. So put them together. I need a saturated design M by M matrix. I want them to have fold over structure. All right? So idea is simple, right? I take U, I minus U. Now because this is square matrix, if this square matrix, this would be a rectangle. That's what we call super saturated design. So I go home, I think I'm pretty good about that. I take my super saturated design, put it there, fold over. It doesn't work because it's singular. All right? Can't do that. So what can I do? Well, if I cannot do that as much as possible. You know, I have some fold over on one side, and whatever necessary, I put the other side. Okay? And I want this part to be big as possible. Got it? I want this part which have all the fold over idea to make it larger. And it came up with theory number 1. You want this metric to be non-singular. You can at most get half. You cannot get more than that. All right? So simple. Now idea was come with, I'm going to have this matrix. Half of them is fold over structure, half of them is not. Okay? That's the structure I have. Now you can see lots of beauty there because the interaction for first group was all orthogonal with second main effect and all the nice properties all there. Okay? The only thing I don't have is interaction among first group, X1, X1 may be confounded. But apart from that, all interaction really pretty nicely done. All right? So what kind of things sacrifice? Well, you first thing take it. So this is probably I just told you all nice property about unconfoundable interaction. Now, if you think about d-optimality, you can think any optimality, which I'll talk to you a little bit. But if you think about d-optimality, determinant of that actually equal to that. So to maximize that, actually what you need to do is maximize both of them. which wasn't too complicated. I just take de-optimal design in the literature, cut and paste, put it there, all right? So if you do that, for example, this is de-optimum for 3x3, so my 6x6 will look like this. Done. I didn't put anything complicated, just cut and paste, put it there, done, all right? Now I present you all kind of nice property against not all of the interaction, but most of the interaction will be orthogonal to many effect. Now what kind of things sacrifice? How large is determined like this? Well, if you think about the so this is what I'm telling you, all the interaction will be free in some way. So think about the efficiency. I think anytime I submit a paper, people complain to me. That's the efficient I love to use. I understand Kiefer's idea needs to divide by the maximum determined and take a ratio. But maximum determined may not know. Some of them may be wrong. I'll tell you why. All right? And Harlem have a upper bound. This is upper bound. This number always between 1 and 0. So that's, I think to me it's easier. But here it's okay. I take my D efficiency, divide by whatever population, what literature you know, see how much I sacrifice. If you do that, you almost lose nothing. Okay? My D efficiency is probably equally high, well at least 90% or even more than the true D optimal. But my design have robust to two-factor interaction, most of them. Got it? Okay, that's a simple idea. Put in there, and I think if you go further on that, so I tell you for that how you assign the group. If two groups, x1, x1, x2, and x2 fold over, most of the variable you worry about should put into the second group, right? And that's the basic message here. And funny enough, when we do, well, there are a few things here. If the traces, if A optimality is what you think, you can put any criterion there. If A optimality is what you worry about, then again, you just put x1 as the A optimality, x2 as A optimality, cut and paste, you're okay. Whatever optimality you put in seems reasonable well. And if you want to change this a little bit, remember what I put there. I have x1, x1. If you want x1, x3, there are something you can play a little bit, make life a little bit complicated, but suitable. Okay? Now there was an accident. The accident was, or take home message like this. If you want to go n by n matrix and you do this for D optimality, what you should do, which I think recommend is better, is have half times half n over 2 times n over 2 in a structure like that. D optimality pretty much preserved, and it was against two-factor interaction very much. All right? Here's a beauty accident. I do that to lot because all I need to cut and paste. I did not invent anything, right? I go to website with all determined metrics, and I cut and paste. I do everything, and I compare with the truly D optimality. Meaning what? I have D optimality of mine compared with D optimality there, right? You know what happened? One of my good friends, Novus, have a website on that. This is interesting. When I equal 94, my design actually beat D max. All right, I need to ask him to revise somehow. All right, but nonetheless, you probably see the D efficiency is not lost much. It's pretty much the same. All right, so that's my first P, about 7 minutes. Okay, thank you. Oh, 12 minutes. Wow, you're good at math. All right, I cannot count. I told you that. Now, second part is about try to do something on. That's a wonderful paper. I realized that in this conference, unless your paper published in JQT, you're not supposed to talk because everybody cited a paper in JQT. So finally, I dig out. Here's a paper from JQT. This is a beautiful paper. It tells you lots of great idea about what you find from practice, and I'll tell you roughly what it's all about. But summarize that because I will be speaker this afternoon, so I think you'll tell more detail. Plus, this is my talk. I'm not supposed to do advertisement for him. So let me do quickly what they hit is. The problem looks like they have a 3-label, many effect and quadratic terms. All right? They want to design against robust interaction, even there's interaction, and they want a minimum point. So you know for minimum point, there are k variable, you need 2k plus 1, that means it runs. Right? In 3-level. The design they proposed looks like this. If you read the table, the paper there, they have m pairs. Each pair is mirror image, and then add another zeros. Got it? All right, and there's a 0 in diagonal. 0 in diagonal there are m pairs. Each pair is a mirror image. All right? And then the computer search. And you know Brad's very good, not only brain, but his computer's better. I was wondering yesterday when this gentleman said, what if Fisher no PC? What if I, Fisher, have a computer? Well, I'm sorry to say, but he would be one of us. Not that great, I think. But nonetheless, it's just opposite. But nonetheless, here's the design I have, and they search a result, give you wonderful, beautiful thing. I'm not going to, here's the algorithm about Jones and Nordstrom. I'll leave Brad to tell you detail, which I don't know much actually. I copy from the paper. All right, so this is the design they find out. From N to 4, 5 to whatever is more. Now, when I come to this sheet, and they even give example how that goes. Now, when I come to see this problem carefully, when I look at this problem carefully, if I reshuffle, regrouping them carefully, it really looks like this, right? You have to take all the top row, put together to see the other was kind of fold over. All right? Now remember what I told you. By fold over, you're robust to interaction. It doesn't matter what C metric is, right? As long as it's a fold over structure, you'll be robust against interaction. So the question is really come to how to find the C metrics, right? Rather than computer search. Got it? Okay? So now question come to a simple thing. Given n by n matrix, which has 0 diagonal, others plus or minus, what's the maximum determinant possible? That's D optimality. You can do something else, but that's D optimality. All right? So look around, it turned out there's something called conference matrix. A conference matrix is a square matrix, diagonal all 0, or off diagonal plus or minus 1, with this property. Okay? So CI is all 0, others all plus or minus 1, and they have property like this. Okay? For example, this is 4 by 4 conference matrix. One thing I want you to pay attention, you probably may notice so far, if I place diagonal 0 to be 1, that's called Hadamard matrix actually. All right? If I put, it's unfortunate UK system, my pen is not synchronized, so I cannot write very well. All right? If you put as 1, you got Hadamard matrix somehow. All right? So we come with a design which is, again, I did not do any theory, I just cut and paste from the history. Right? Here's conference matrix put there, send to Brad and say, look, this design looks better. I send it out, all right? So it looks like if this 4 by 4 conference metric, I take the first 4, fold over that, plus 0. That serves purpose very well. So if you do that, here's the property, right? All the many effect, and in this case, will be orthogonal to each other, even better, and robust to two-factor interaction. Okay? So this 12 by 12, the reason I use 12 is big, because in my design here, the D efficiency 92.3% compared with reported in the papers 89. Without computer, just cut and paste. You know what to copy conference metric, just put it there. That's all it takes, all right? So we compare a little bit. Well, to pick a paper publisher, you need to do a thorough study to convince them you're good. So you take a ratio, if you do that, up to 10, we are the same. The design we have is the same as what Jones and Nordstrom published over there. Bigger than 10, our D efficiency is much higher. Okay, and without, you don't need brain, you just need a pair of scissors, cut and paste, that's all it takes. All right? So I'll tell you more about that. 22 is not available. Apart from all the even number, we are better. And if we think about this full second order design, then our D efficiency is also higher. Not only first order or second order, if you put there. So that's, again, you want to put some pages people cannot do too good, right? You know, I getting better? That tells you what the property we have, and more detail about what the matrix form looks like. Here's the design I have. If you do that, what kind of thing that you're going to happen, and we'll study those metrics carefully. All right, here's a few things. Number one, conference metric only exists when M is even. Even that is not quite true. All right, that's one thing. And I'll tell you more detail about conference metric, which are getting more interesting on that. If you odd number, well, there's a couple things you can do. You can not so minimum, just delete by one column for larger one, or you can use the one report by Jones and Nordstrom, because I don't have anything to replace on that. Now, confidence metric also a special case for winning design. I know lots of experts in this audience, all right? And I think pretty sure that something might be able to work it out if given the background winning design put in here, and maybe something interesting for you to think about. Let me say a few words about confidence metric because I got 5 minutes to kill. I get my conclusion, right? So anytime I can stop here. So the basic idea, confidence metric is C transpose C is M minus I times identity matrix. And all diagonal will be 0, off diagonal will be plus or minus 1. So originally, this is what it came from. I don't have time for the history. So when M is multiple of 4, confidence metric very relate to Hadamard matrix in many ways. If N is 4t plus 2, even but not multiple of 4, it has to be symmetric, all right? And it will exist only when n minus 1 is the sum of 2 square integers. All right, for example, those are numbers. 6 minus 1 is 5, 5 is 1 plus 4. In American, UK, this proper consistent, so it's pretty much the same. So those exist. 22 doesn't exist because 21 is not sum of 2 squares. All right, so there are a few things there. So if you're interested, confidence metric is still lots of things about construction, how to handle that. So here's an example published in our paper. Let me link something together. I think lots of people work on Hadamard matrix. One thing they're doing there is tells you if I have an n by n square matrix whose element is plus or minus 1, what's the maximum determinant possible? That's simple version about Hadamard metric. The contribution from Hadamard, of course, he proved that any metric satisfy this equation will be, and it's only happened when n is multiple of 4. This called Hadamard metric or something we call Prackett-Berman design. One stage, Norman Draper and I published lots of papers on Prackett-Berman design. And Norman even tell me, Dennis, I think we know more about Prackett-Berman design than Prackett-Berman in some way, but I think that's not true. Anyway, and the bound has been extended for 40 plus 2 for even number. For odd number, that doesn't seem to have very general rules. Okay, every matrix seems discovered by all independent theories. So you can have a paper n equal to 11, boom, whole paper just tells you I find 11, all right? Because there are no general rules. Now copy that, that's all done. Copy that to what I'm doing right here. I'm asking the very similar questions. If I have n by n square matrix whose diagonal element is 0, off diagonal plus or minus 1, what's the maximum determinant possible? And that's what I'm going to using in my design, right? Okay? And it turned out if n is even, some results possible for 4t or 4t plus 2. But really interesting what happened, the odd number. If n is odd, the opportunity is great because anything up to 11 seems they claim, they didn't prove it, it seems claim that they found something. But above 11, there's nothing available, which is reasonably small for you to do something about it. All right. Let me remind you, 11 itself is one paper, 9 itself is one paper. You don't need the general rules. All right. So this is something interesting. So I think looking ahead, if you look at the future, there'll be whole lot more confidence metric application in some design special setup, which we didn't using too much. Second part is more about construction of so-called confidence metric. You want to determine to be maximum, diagonal to be 0. And there are a few more things, lots of things can be done there. So we try to prove something called equivalent theory. I'm sorry, this is wrong, abuse the word. I know it's not optimum design people imagine. If you have n by n square metric, elements plus or minus 1, what's the maximum determinant possible? Here's part B, given n by n square metric diagonal 0, what's the maximum determinant possible? We try to show a conjecture that solution for A and solution for B are somehow related. Okay, they make some one chance to the other, and that's what we try to prove somehow. So if you have any question about this, one good reference is Peter right over there. If you got any question about confidence, don't ask me, ask him, all right? So let me give 1 minute quick review about finally the minimum point design for full second order model. Here's main effect, here's quadratic, here's interaction. All right, there's something on that. I'll skip this part. Let me talk you about spanking. Now, original box spanking design marry two things together. The BIBD, balancing complete box design, and full factorial design putting together. For example, here's 4 variables put into 6 blocks. You have each star here, this one you replace by that, or else put 0. Got it? That's box bending design. Long, large, yes. Now what we try to find here in this small paper, small work, I try to say, well, if I take treatment number equals 3, and instead of 2 cube full factorial, I use fraction factorial. 4 run rather than 8 run, put into that. Then you can squeeze the wrong size nicely, and most of the problems still keep nicely. All right? And that's basically what this paper is all about. So let me conclude here. Thanks again for the committee. Thanks again for Steve, Rosemary. Thank you so much. For those people who, after 2, you come to Cambridge, you have to go to London, right? I only one cent for you. If you go to London, London is a very complicated place. You need a map. It's very complicated. But what I realized after this 7 weeks, go with my family, if you go to London, you better have a BMW. All right? You need to take a bus, take a metro, and you need to walk. Okay? So make sure you have BMW with you when you go to London. Okay? By that, if you got any question at all, I still same thing. Send me $500. I'll tell you the detail. That's my email, just in case if you're interested. Any problem or any reprint paper, I can send you. All right. Thank you very much. Appreciate it.
Time for 1 or 2 quick questions.
Yes, Steve.
This is clarification really in the first part of your talk for the first order model. You were saying that having as many columns folded over as possible gives you more robustness. But if I understand correctly, the D-optimum designs for n equals 2 mod 4 already have that structure that you showed. So we've got x1,
Yes.
x1.
Yes.
So you can't do better than the
Multiple 4. If run size is multiple 8, that's for sure. You can take a packet boom design or hollow metric to fold over.
No, but if it's a multiple, if it's n equals 2 mod 4, then I think
2
the
mod
D-optimum
4,
designs have
I
to-
don't think so. That's why my 94 with the MX, right?
Isn't that what the Ehrlich paper shows? You have to choose the x1 and x2 carefully. But I think the D-optimum designs have exactly that form. For
Yes.
numbers where
Even number.
for even numbers.
Yeah, it must be even number because my
But not
construction,
multiple.
the run size must be even, that's for sure. Yeah. I will
Well,
talk-
we can check that.
Sure.
with you.
Another quick question.
Yes, Andrew?
Okay, so a sort of philosophical question. So if you are running an experiment, you're fitting the main effects, and you want them orthogonal because there may be interactions, shouldn't you be fitting the interactions?
Okay, that's a good question. I think we try to, I don't know my time, I do have some joke about screening. Some funny cartoon about screening. When you do screening, actually you don't have much cost is low. And if you agree with Jeff's spin of first aid, he talked about if your interaction exists, your main effect must exist, for example, if you make an assumption. Now this is nothing wrong. You can unbiased estimate for your main effect for further follow-up. If you think anything related to that, you can run your interaction. But in general, yes, you've got money, you think more about they should not go first order model. And my problem is not it.
You're calculating your d-optimality, if I understood it right, you're calculating that on a first order model.
Only of first order, yes.
So what might be quite interesting is how well would they, how well
If they include the
perform.
interaction.
Yeah.
That would be, the metric will be singular. I don't have money for that. That's minimum effort.
Then you wouldn't be able to fit the interactions if it's.
I would not able to. I need to do some follow-up for sure. All I'm saying here, I will get unbiased estimate for main effect. What the optimum may not. That's the only thing I can kind of.
Okay, I think we have to move on to the next speaker. Let's thank Dennis
Thank you very
again.
much.